Welcome to this lecture series in real analysis. We have defined the geometric definition of differentiability and the notion of derivative. In this lecture, we will talk about the analytic definition or the analytic theorem, if you will, of derivatives, which is more traditional as found in textbooks. It is defined as the limit of this kind of a function, fx minus fa divided by x minus a. So if f is a function from some interval to r, then the derivative at the point a is defined as this limit if it exists. Typically in textbooks, this is how it is done. But we have already given a definition of the derivative using some cones and whatnot. So I will not be recalling all of those details. So let us recall at least a few things. The epsilon cone about a right ray rho starting at the point a comma b. So this is a rho starting at the point a comma b. This is a ray starting at the point a comma b. I think I said rho. Let's say its slope is m. Slope meaning the tangent of this angle. So this was defined as that, right? What is the idea? You pick some theta with that constraint. It is close to epsilon. And then this, as x is greater than a, is just the set, or is just this ray whose slope is theta. And starting at the point a comma b. So all you're doing is you're collecting all these rays whose slopes are within epsilon of the slope of the right ray that we started with, and that forms a cone-like object, and that's why we call it a cone. The parameter epsilon features here. Okay, then we defined one-sided differentiable functions, and then by extension two-sided differentiable functions, and we defined derivatives. So what were differentiable functions? A function f defined on an interval, and a is a point which is not a right boundary point. Then we say f is differentiable at a if whenever f is differentiable at a if there is a right ray starting at the point a comma f of a. So here b becomes f of a starting at the point a comma f of a, such that whenever you draw an epsilon cone about this ray rho, there is a delta greater than 0, such that the graph of the function in this region a comma a plus delta is contained in the epsilon cone. So all of this requires a picture and all, and we did this in detail, so I'm not recalling everything. So that was the definition of differentiability, and the derivative was the slope of this right tangent. We showed that there is going to be such a unique right tangent, and its slope is called the right derivative of the function. And by extension, one can define the two-sided versions and the left versions of the same concepts. We of course need to know what is meant by limits and continuity and this one-sided notions of those. Mainly our focus is on two-sided notions, but it is just easier for me to explain the one-sided version, and the two-sided versions are just analogous. So I'll prove everything in the one-sided way, but we really care about the two-sided versions. Okay, so first we'll prove a lemma. It's not much of a lemma, it's a triviality, and we gave this as an exercise in the previous problem set. What does it say? It is just, we are just kind of rewriting the epsilon cone in a different way, in a very, very slightly different way. So you pick a point a comma b in R2, and rho b a right ray starting at the point a comma b, and suppose m is the slope of the ray. Then for epsilon greater than 0, we claim that the epsilon cone about rho is nothing but that set. And let me just justify this visually. I do not want to give a formal proof of it. So I have drawn this ray starting at a comma b. And suppose I pick a point in this set. I want to show that any point in this set is in the epsilon cone and the converse, but the converse will be as clear as this one. So okay, I pick a point x comma y in the set. Let me mark a point somewhere, let's say here, that's x comma y. And what am I given? I'm told x greater than a, that I've already accounted for by drawing x to the right of this point. And I'm also given this condition. How do I understand that condition? So y minus b and x minus a. Y minus b is this length, and x minus b is that length. Let me draw it. That's y minus b, and this is x minus a. So this ratio is nothing but the slope of this line, y minus b divided by x minus a. And we are saying this slope, let me draw that line. We are saying the slope of that line that I just drew is not very far away from the slope of the starting ray. It's at most, it is less than epsilon far away from it. So that's exactly what the epsilon cone was. It was the collection of all those rays minus the starting point, because we do not want to put the starting point in the cone. The apex of the cone is not in the cone. So it's just the collection of all those rays which have their slopes within epsilon of the slope of the original right ray. So it's a triviality, but if you really want a proof, you can write it down. All right. Now for the main theorem. In this slide, I will explain it intuitively, but in the next slide, I will prove it formally. It's a lot of things written here, so I apologize for that. Fix a function f defined on an interval I. And suppose a is a point in the interval where a is not the right boundary point. These are our usual hypotheses. So a picture has been drawn. And we are saying that the following two things are equivalent. The first thing is that f is right differentiable at a. And the second is that this right limit exists. And further, this limit is same as the right derivative of the function at a. So this statement should have been clubbed there. It seems like a standalone statement. I meant to have it as a part of the second one. So I hope the statement is clear. Let me talk about this quantity a little bit. I'm sure you're familiar with it from high school, because of high school physics maybe. So what is this quantity? Well, you pick a point x towards the right of a. Then what is that length? That is fx. And when I say length, I mean signed length. So that whole thing is fx. And similarly, this is fa. So this ratio is nothing but this length divided by that length. So it is sort of an approximation to the quote-unquote the slope of the tangent at the point a comma f of a. Right, that's kind of an approximation, but if you take the limit, that should become the true value. And that's the intuition behind this definition anyway. This is why such a definition is given. But we define tangents in a different way, in a slightly different way. So this is no longer a definition for the derivative. This is a theorem now that the function is right differentiable if and only if this right limit exists, and the right derivative, which is nothing but the slope of the right tangent, is same as the value of this limit. So let me explain this intuitively, and then in the next slide we will give a formal proof. So let's first talk about this direction. Suppose f is right differentiable at a, which means that there is a right tangent to the graph of f at the point a comma f of a. So let me draw that right tangent. So there is a right tangent, call it rho, and let's say it has some slope, call it m. Okay. Now we want to show that this limit exists. It's another matter that that limit will be same as m. So yeah, so we'll claim that this limit is actually same as m. That's not another matter. That is what we claim. We claim that this limit exists and is equal to m, the slope of the right tangent. What do we need to do for that? We need to talk about this difference. We need to say that this difference becomes smaller and smaller as x approaches a from the right. As x comes closer and closer to a from the right, this becomes smaller and smaller and smaller and becomes as close to 0 as we please. That's what we want to do. Alright, fine. So suppose we want to show that this is at most epsilon. So fix an epsilon greater than 0 and draw the epsilon cone about this right ray. Alright, that's the epsilon cone about the right ray. By definition of right differentiability, we know that there is a delta. There is a delta such that for all points within this right deleted delta neighborhood, the graph of the function is trapped in this cone. For every point in this delta, right deleted delta neighborhood, so we get a delta. And now if we pick any point here, call it x, the corresponding point in the graph will be, the picture is kind of misleading, so let me not draw the graph of the function because then it would be a problem. So the corresponding point in the graph of the function will be somewhere in this cone. Let's say that point. So this is x comma f of x. But now by the virtue of the fact that this is within the epsilon cone, it just says that the slope of this particular ray starting at the point a comma f of a, passing through the point x comma f of x, is within epsilon of m, which says exactly this. It says exactly this statement. So that proves 2 from 1. And if you just reverse these steps, you will get 1 from 2. Okay? So that's the intuitive explanation. We can just see it. There is no mystery behind it. But if we really want a formal proof, we will give it now. And in the course of that, we will also prove an interesting extension of this theorem. It's actually very useful. So we should not take that lightly. So here is it. The previous thing has been written, but there is an extra thing that we want to say amongst our equivalences. The following are equivalent. The first two are from the previous slide. The third one says that there is a function a defined on the interval I such that a is right continuous at the point little a. I know, horrible notation. This is little a, that is capital A. Horrible notation, but forgive me. With the property that this happens for all x in the interval I. Okay. So why is this? Let's do 1 implies 2. So we want to show that this limit exists. Okay. So by 1, f is right differentiable at a. So say the right derivative is m. All right. And now we want to show 2. So fix epsilon greater than 0. Want to show that there exists a delta positive such that this happens for all x in this right delta deleted neighborhood. Right, this is what we want to show. But now by the fact that f is right differentiable at a, by 1, we know that there exists a delta greater than 0 such that the graph of the function restricted to this right deleted delta neighborhood is contained in the epsilon cone about rho, where what is rho? Rho is the right tangent, rho is the right ray starting at the point a comma f of a with slope m. Let me write that. Where rho is the right tangent to the curve, but the more descriptive way of saying it is that rho is the right ray starting at a comma f of a and having slope m. So we want to do that. So we want to prove the blue thing. And we have this by 1. What does that say? So thus this ratio is within epsilon for all x in this right deleted delta neighborhood. What just happened? We use our quote-unquote lemma that we talked about. If you just use our lemma, so it shows that the epsilon rho is some set, whatever that set was. If you just use the definition, you'll get this. Okay. So, yeah, this proves 2. And now we will do 2 implies 3. So, fine. Or 2 implies 3. So, we will just construct that function. So, define this as ax as so that's our definition of the function a. Clearly this happens for all x in the interval, right? Because if x is not equal to a, then we can just take this to the other side because this is non-zero and that matches. If x is equal to a, both sides are 0. Doesn't matter what the value of ax is. But the point is, a is right continuous at a. That's why this was a horrible notation. I mean, capital A is right continuous at little a. Simply because the limit of ax as x approaches little a from the right, this is what? This is this limit by definition of the function capital A. This is that limit, but this is equal to the value of capital A at little a. And therefore, capital A is right continuous at little a. And this is one of the things that we discussed in one previous lecture. So A is right continuous at a, and therefore this proves 2. Right? This was exactly the statement of 2. And now 3 implies 1, and this will finish the proof. Okay. So to do 3 implies 1, let m be the value of capital A at little a, and rho be the slope. Rho be the right ray starting at a comma f of a and having slope m. So we claim that rho is the right tangent to the graph of f at a comma f of a, and that will prove 1. Maybe one picture is useful. Right, this is rho. So to prove that this is the right tangent, we'll take epsilon positive. And to prove this claim, now we need to show that there exists a positive delta such that the graph of the function restricted to this right delta deleted neighborhood is contained in the epsilon cone about rho. I've drawn the epsilon cone. All right. So by the fact that capital A is right continuous at little a, we know we have a delta greater than 0 such that ax minus aa is less than epsilon whenever x is in this region. Right? But what does that say? It says, by definition of the function capital A and by definition of little m, right? This is little m, and ax is that expression when x is in that region. And this shows you that this containment indeed holds. That's it. So here I'm just being a little bit frugal with the details, but I'm sure you can fill it up. This theorem is not at all a hard theorem. I just gave all the intuition in the previous slide. Previous to previous slide. But here I just wanted to write down a proof for completeness. All right. Let's compute some things. So we have this function, which is the identity function. What about its derivative? Does it have a derivative, etc.? So let's talk about the right derivative, and the left and the two-sided versions will be left to you. So at x equals 2, so we want to talk about the right derivative at 1. Does it exist, etc.? So to do that, we just need to evaluate this limit, or think about this limit. Let's see if it exists. But what is it? By definition, this is which is equal to 1, clearly. So indeed, this is a differentiable function. This is differentiable at 1. What we have shown is that it is differentiable at 1, and its right derivative at 1 is 1. But it is actually differentiable everywhere, and everywhere it has derivative 1, and you can compute it. That is an exercise. It has two-sided derivatives everywhere, and the derivative everywhere is 1. What about the squared function, the squaring function? Let's again compute the right derivative if it exists at 1. So again, we are dealing with this limit. Which is nothing but that expression, but this cancels away. I meant to write 1 plus, which is equal to 2. So it has it is right differentiable at 1, and the right derivative is 2. But it is actually two-sided differentiable at 1, and its derivative is 2. That you can prove by computing the left derivative. And in fact, it is differentiable everywhere. It's not like it has derivative 2 everywhere, but it is differentiable everywhere, and you can prove that with the same kind of argument. And in the coming lectures, we will have a more robust way of computing derivatives. We will show that every polynomial function is differentiable, and we will find an expression for the derivative function. So just to finish, there is a two-sided version of the theorem that we just stated. Just for the record, I've just slashed out the right everywhere. That's it. Alright, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.